everyone. Today we're going to start with lesson 3.3, vision. And by the end of the lesson today, you will be able to determine how important perceptual interpretation is to our experiences. So that means, how is it that we interpret vision, and how does that impact our experiences?
Okay, hi everybody. So we're going to talk about vision and how vision works. And first, to understand vision a little bit better, we should understand what it means to transduce or what transduction means. So transduction is when you take energy, in this case it's going to be light energy, and then you turn it into a neural message. So we remember how we talked about how neurons transmit information. Those neurons also will transmit sound. And so sight. So when the light enters in through your eye and goes to the back of your retina, that information travels through your optic nerve through neurons and then into your brain to either the right or the left so that you can process what you are seeing. So in this case, what is going to happen is the light is going to transfer in through the pupil. And so this is how vision works, right? So vision works by light entering the eye. And then what happens here is that through the lens, a process that we call accommodation. And what accommodation is going to do is it's going to allow you to focus. So it can focus on items close and far away. So those of you that wear glasses, the reason why we have to wear glasses is because our lens does not focus things properly. So we wear what we call corrective lenses, whether that's contacts or glasses. Those are lenses and they help correct our original lens, which doesn't allow us to focus items on our retina properly. So the lens allows us to focus our item or focus the item, in this case it's going to be the candle, on the back of the retina. And the retina right here is on the back of your eye, and it's very thin, and it's about the size of a postage stamp. And what we have on the back of the retina is called your fova, and it's the point of central focus. So when we focus on something, it's focusing on our fova. Our retina is full of what we call rods and cones, and we're going to talk about those on the next slide and exactly what their responsibilities are, but they help us in the vision process. Once this item, or once in this case it's the candle, focuses on our fova or in the back of the retina, the information then travels down our optic nerve into the visual cortex. Sorry, I kind of drew over the optic nerve there without meaning to do so. So it travels through to the visual cortex. Your optic nerve is full of what we call ganglion cells. So ganglion. Sometimes this comes up, so it's just nice to know. Ganglion cells, what makes up the optic nerve. Now, one thing to note is this right here where the optic nerve enters into the retina is actually a blind spot. So if something falls on your optic nerve or on your blind spot, then you will not see it. And you can notice that sometimes if you cover up one eye and shift around, things will sometimes fall into your blind spot. But because if you have two working eyes, your eyes are constantly moving, even if you're focusing on one thing, they're still shifting ever so slightly, so you never really notice the blind spot. So how exactly does this light come into our eye? Well, it comes into our eye by wavelengths, right? So there's wavelengths that come into our eye, and these wavelengths are important because it helps us see different colors, see different brightnesses. So if you have a wavelength, the brightness, how bright something is. So if it's fluorescent pink or regular pink, that depends on the height of the wave. So brightness is the height of the wave. The hue, so how deep of a color something is, so if it's a really like deep blue or a light blue, is the length of the wave. So this deals with the length of the wave. And so this is how we see. Okay, so vision, brightness, and color. So we just got done talking about the wavelength, and I wanted to talk about that first because that's going to help you understand the rest of this. So we know that the different wavelengths have different meanings, but what exactly in the eye allows us to process those wavelengths? Well, in the back of the eye, there is the retina. And on that retina, and this is actually what the retina looks like right here. Whoops. And in that retina, we have different receptors, and those receptors are responsible for receiving that wavelength and then interpreting it into the information. Again, we call that transduction. So transduction is taking that wavelength, taking that light, and then transducing it into something that we can understand or we can process. So inside of our retina, we have here is a cone, and that is this blue guy. The blue guy is the cone. It kind of has a cone shape. And then we also have rods, and rods are the ones that look a little bit more like that. And then this is the ganglion cell. Remember, the ganglion cell is what makes your optic nerve. Okay. So what does our rod do? Well, the rods are responsible for brightness and black and white. If you turn off the light, so if you've been in a room and you turn the lights off, and it's going to seem really dark, and it may take a minute or two for your eyes to adjust. And same thing, if you wake up in the morning and it's still dark outside and turn on your light, it may seem extremely bright and it's going to take your eyes a minute to adjust. That's because your rods are adjusting, and we call this adaptation. Adapt to light and dark. Now, your cones, the way I remember cones is cones see color, CC. So cones see color, but we don't exactly know why we see color. There's two different theories. There's the trichromatic theory, and what the trichromatic theory says is that we see red, green, and blue. And we see these in different formats, and these colors combine to make all the colors that we see. So that really we have cones that see red, we have cones that see green, we have cones that see blue, and depending on the wavelength and the wave height, depends on what cones get activated, and that's how we see all the different colors. But what it doesn't explain is what we call an after image. And unfortunately, I don't know a good way to show you after image on the computer other than to tell you if you can look at something red for like a minute or two, so look at something really bright red, and then close your eyes and look up at a light, and then you'll see something green. And that's what we call an after image. And trichromatic theory cannot explain that. So we use what we call opponent process theory. And what opponent process theory says is that we have cones are paired and they cannot fire at the same time. And this would explain why we don't see a red-green color, right? So we might see a green-yellow color, but we do not see a red-green color. So this is going to explain that we have red-green cones, that we have yellow-blue, and that we have white and black. All right, now the last part of color that I want to talk about is color blindness. So if you look over here, this is a typical test that they use for color blindness. If you can see the 5, then you do not suffer from color blindness. But color blindness is a genetic defect in your cones. So there's actually a cone genetic defect is why people suffer from color blindness. So now that we understand how vision works, let's talk a little bit about perception of that vision. So first off, we have what we call perceptual constancy or consistency. And really what that means is that we perceive objects as unchanging. And this allows us to identify things quickly. So if you see a building, like if you're driving into Washington, D.C., and you see the Washington Monument, when you're far away, it looks small, but as you get closer and closer, it gets bigger and bigger. Well, we know that the size itself isn't changing. We know the idea of the fact that it is the size it is, and it helps us recognize things quickly. And this can be broken down even further into what we call shape and size consistency. And that means that even if you see something from a weird angle, you still know what shape it is. If you see something far away or close up, you still have a good idea of what size it is. And we can even do this with color. So if you see something in the dark, we still know that it is blue, or we still know that it is yellow. So even though it looks a little bit different in the daytime versus the nighttime, you still understand what color it is. So we perceive objects as having a constant color. Now, something that's kind of interesting though is that this perception can be altered, right? So if you take a look at our board game right over here, or a thing right over here, you see box A and you see box B. It's not as easy to do on the computer, but box A and box B are actually the exact same color. What? I know, right? So normally what I do is I have this printed out on paper and I make the kids cut them out and put them next to each other because nobody ever believes me. But if you were to print them out in the original picture, it may not print out perfectly because it's been copied and pasted multiple times at this point in time, but it is the exact same color. And what's throwing it off is this green cylinder right here. So the placement of the green cylinder and the shading around it is what makes us think that that color is different. So it just shows us how we can really change our perception. So visual information processing. So we know how we see, we know how perception can be impacted by how we see. How exactly is all of this processed? That transduction, right? From sensation to recognition. So if we have a scene, in this case, it's a man playing a unique looking flute. So the first thing that's going to happen is our eyes are actually going to work, right? So we're going to have a retinal processing. That vision, those wavelengths are going to go into the back of the retina. That retina is going to process that. What happens then is what we call feature detection, and this is important, so you may want to write this down. It's the brain's detector cells, so it responds to elementary features, bars, edges, or gradients of light. So what exactly does that mean? Well, it lets us really understand and see the specific details of the lines and edges. So in this picture, the idea of understanding like the shape of the flute or the differences in the face with the nose and the underneath the eyes. So think about it as it helps us understand the different features. So if I have all of you lined up and I look at all of your faces, every face has different features because of the way that the lines and the angles of all of your faces are slightly different. We're all human, but yet we all look different. That's the feature detection. That's how we can tell the differences between different faces. It then goes into abstraction, our higher level cells combine to process the feature detection. So you would say, oh, I see that bass, or I see that instrument, I play something similar, or I've never seen something like that. So now we're thinking higher processing. And finally into recognition. Do we recognize this or not? This all happens in parallel processing. So we talked about dual processing, where we have the two lanes, the upper and the lower, and the upper being things that we're aware of, and the lower being things that we're unconscious of, right? Well, the parallel processing is the upper part of the dual processing. And what this is saying is that even can be done. We can do multiple things at once. So we can notice color and movement. So that's both dealing with the visual process. I can see my ceiling fan right now is a dark brown. I also can tell that it's moving around. So that would be the parallel processing, the upper road of that dual processing.